Our next presenter is Sandra Baurier, and she will be presenting the genesis and localization of the Ni-Cu-PGE sulfide contact ores. So take it away, Sandra.
Okay, thanks, Marina. Good afternoon, everybody. And thank you again, as Dustin said, to be here listening to us. My name is Sandra Baurier, and I'm also part of the Sudbury team. And I'll be presenting, in this case, basically a review on the genesis and localization of the Ni-Cu-PGE sulfide contact ores in Sudbury. So just to take it away, Dustin already showed some timeline regarding the different resources that we find here in Sudbury. But again, to highlight why is Sudbury important to us. So it basically, it's one of the largest Ni-Cu-PGE camps worldwide. And as you can see here, located in southeastern Canada, it basically has pre-mining resources that exceed 16,050 million tons and approximately a ratio of 1:1 nickel-copper, 1.2, 1.1 copper, also some minor cobalt, and again, palladium platinum. And here, as you can see, they basically are surrounded by the big camps, such as Norilsk, Jinshuan in China, and other ones, such as Thompson. A very brief geological overview of what I'll be explaining. Dustin already went and explained the main mass, some of the footwall rocks that we're presenting in both Superior Province and the Southern Province. However, in this case, the takeaway of this slide is where are the contact ores, or where is Sublayer Norite and the Footwall Breccia located? And as you can see here, this type of breccias, magmatic breccias, they're located discontinuously along the basal contact of the SIC. Most of all, they occur as continuous lenses or sometimes sheets, in this case, Footwall Breccia, but they're located normally in embayments or troughs in this case. It is also important to highlight in this case that Footwall Breccia is normally more present in the North Range rather than the South Range. So let's go deeper into the contact type deposits or contact type environments. And here we have a brief scheme of how it looks like. So we have our main mass, we have our mafic norite, felsic norite here, and we have Sublayer Norite that overlies Footwall Breccia here. So the issue is that the transition between Footwall Breccia and Sublayer Norite normally is gradational. And as you can see here, or as Dustin also explained, contact ores normally host most of the nickel mineralization in Sudbury. They're nickel rich, not so much copper rich. And normally mineralization hosted in these breccias can be either massive, semi-massive, to disseminated. We have some average ore tenors, as you can see here, 1:1 ratio, nickel-copper, and then up to 5 to 10 grams per ton of palladium platinum. I'm not going to talk about Footwall type deposits or environments in this presentation. Again, it's a lack of time, but just to highlight very briefly, the transition between the contact type deposits and the Footwall type deposits is again transitional, it's gradational. As you can see here, we have from more nickel sulfide rich melts to more fractionated copper rich sulfide melts at the footwall. Normally these occur as veins, they're massive, stockward, also disseminated, but the ore tenors are a bit different. And again, we have an enrichment in palladium platinum in this case. So very briefly, what is Sublayer Norite? As we said beforehand, is a magmatic breccia, in this case as an atelolithic breccia, that is described or can be defined to have a noritic matrix that can be variably infiltrated by different amounts of sulfides. Sometimes we'll find Sublayer Norite mostly consisting of massive sulfide, very low amount of clasts, or basically noritic matrix. And then on the other side, we can see some sublayer, just like in this image of the Levack embayment, with very few sulfides. What about the inclusions in this case? Well, we have 3 different types. We have local, we have cognate. These are derived from the main mass itself, and we have exotic. The exotic class, normally we're talking about ultramafic clasts, and they're more common, or basically they would represent for us now kind of a vector for mineralization. So when we see ultramafic clasts, watch out for the sulfides. And as you can see also in these pictures, just like some transition from sulfide-rich sublayer to, as we said beforehand, sulfide-poor sublayer. However, what about the Footwall Breccia? Well, this breccia is a bit different. One of the main differences compared to sublayer is a type of matrix. And why? Footwall Breccia presents an atectic matrix, so it's basically derived from partial melting of the footwall rocks. Again, it can be variably replaced or infiltrated by sulfides. but the inclusions that we find, also the 3 of them, local, cognate, or felsic, we have to look for a high population of the local clasts. And in this case here, in these images, we can see some examples of Footwall Breccia from the South Range Highway 144, where we can see this metabasalt clast within this granitic matrix, or here too within the Whistle embayment. So what about the styles of mineralization? We were talking beforehand that contact ores normally range from massive to semi-massive and then disseminated. However, here, just some pictures. We have disseminated and racked. Normally we say this when we have an amount of sulfides that oscillate between 1 to 5%. And this picture here from Sublayer and Craton Mine embayment, we can see that we have this nickel-rich sulfide assemblages, for example, pyrrhotite, probably penlandite, and lesser chalcopyrite in this case. We also have other styles, as we said beforehand. One of the most common styles that we see in drill cores or in samples or in sublayer would be basically inclusion-rich semi-massive sulfides. And here we have some transitions. We normally expect, again, in these environments to have nickel-rich mineralization. So again, most of the composition or most of the sulfide minerals will be pyrrhotite and penlandite with lesser chalcopyrite. And here we, again, see the same thing. So we have this metabasalts, maybe some diabase clast, some gabbros, some intermediate clast over here. But again, the matrix in between of it, it's mostly consisting of pyrrhotite. However, we can sometimes find the other end member, we would say. So we find lesser clast, we have a sublayer with a major sulfide component in the matrix. And what we find here in this case is that we do have more chalcopyrite. So sometimes we have this local fractionation too. Well, this picture is not really about contact environments. This is Footwall type, but however, I had to put it because it's pretty amazing. And one of the issues, as we said beforehand, remember that the transition between contact environments to Footwall environments is gradational. So we have this increasing again in fractionation. So we have copper-rich veins or melts at the end formed, and then ultimately this massive chalcopyrite, for instance. And this is one of the amazing pictures we have in the Podolsky Footwall deposit. So now I'm going to talk about a bit the different models of formation that are related for our sulfides or to our mineralization. So basically here in Sudbury, most of the models that we have are suggesting the following, that our ores are basically produced by gravity segregation of immiscible or dense sulfide melts that come from the main mass, then they're settled into the SiC basal contact, and they might be later swept into topographic embayments. This can be by convective currents, can be by gravity-driven dense flows, etc. However, this model has several problems. If we look at it, we're going to talk about later about the isotopic variations for sulfur, osmium, and lead. These variations do not only vary in ores and different types of ores, but they vary between different ranges, different deposits, and even between the same deposit. One of the other problems we'll address will be the initial concentration of sulfide in the melts. That is a problem because it is still unknown. And then there are other ones that, due to matter of time, I won't be able to talk about in this presentation, but please feel free to, again, email or just ask. So we have two end members for the formation of Sublayer Norite and the contact ores. I'm not including Footwall Breccia in this presentation because that would be another 15-minute presentation. But however, we're going to take Sublayer Norite kind of as a whole for this kind of environment. So model one, what does it propose? As you can see here, we have a brief schematic of what would be the main mass and the footwall, and we have sulfur-saturated horizons or regions through our main mass. Over here in the upper part, down closer to the footwall, basically in areas where we have cooler melt sheet. So in these areas, we're basically exsolving the sulfide droplets and basically settling them into the basal contact with the footwall rocks. Later on, we might have this migration into this topographical embayments by these convective currents, or again, we said beforehand, by these driven dense flow. Later on, when these ores are settled in our embayments, we might be able to modify them by assimilation of sulfur and lead from the local country rocks. However, we have the other end member. This is one of the models that we are currently as a team working on. and involves the following thing. As you can see here, one of the main differences is that we don't have a sulfur saturated melt sheet. We have a sulfur undersaturated melt sheet. What happened here? So we're implying that during impact, we're devolatilizing certain elements. For example, lead and sulfur, one of them. This occurs prior to homogenization of the impact melt. Later on, because we are not segregating sulfides from the melt, we have to acquire them from somewhere else. And how is this possible? We're implying with this thermomechanical erosion that basically would take place at the basal contact with and erode or gobble up the footwall rocks. We would then form this immiscible sulfide shenomelts. Of course, the antoliths here derived from the melt sheet, exotic glass maybe coming from somewhere else. And later on, this debris flow, or basically these smaller sulfide droplets would be even able to move by this convective currents and again accumulate here in this area. Remember that by thermomechanical eroding our rocks, we're assimilating also the components such as like sulfur and lead from the footwall rocks. So very brief concept of what is devolatilization when I was mentioning this. So, well, here we have our mass concentration or mass concentration ratios of the elements in CM chondrites over CI or C1 chondrites. They're the same thing as a function of 50% condensation temperature. So a take all of this slide is basically that we can group our elements into different aspects. For example, we have a group that would be the refractory elements, other groups that correspond to those moderately volatile elements, and then we have a group 2 that are highly volatile. As you can see here, at high temperatures, we're able to lose certain elements. And look at what we have. We have lead, sulfur, zinc. In this case, we're talking about that we'll refer to later. This is in a condition of a nebulosa, really. So for oxidized conditions, we're assuming that osmium is more volatile that presents in this figure. Let's talk about now this variety in the isotope system. So sulfur isotopes, as you can see here, we have a considerable variation occurring along the north and the south ranges, south range ore, north range ore, one of them being less radiogenic, south range than the north range. We have also a difference between the south range, the ores or the different regions and their norites too. And not only this, we have also like a variability in different south range deposits too. So again, one of the things that we're implying here is that the sulfur cannot come all from the same place, so the main mass. So some of the sulfur has to interact with something else. In this case, we are suggesting the footwall rocks. On the local sources for sulfur that we've seen, such as the protoors, would be normally in the Pissing, Eastbow Lake intrusions, the Levack suite of mafic intrusions, and then also the Uronian metasediments from the south range. So now let's go into the lead isotopes. Again, the lead isotopic composition of the ores is widely variable. And one of the things we'll be able to see here is, for example, the north range ores, such as here, are less radiogenic than the north range main mass. However, if we look into the contrary, we find that the south range contact ores are in fact more radiogenic than the south range main mass. So as a whole, we can see also that north range contact ores and main mass themselves are more juvenile than those in the south range group. What else do we see? Well, that the local north range footwall ores are more radiogenic than the north range contact ores and the main mass. Thus, that probably we have a slight Huronian component that was indeed in place in the north range at the time of the impact. Another thing that we might be able to observe is that, for example, the north range mafic norite is less radiogenic than the north range main mass here, thus indicating that we possibly have some contamination, assimilation by lesser radiogenic mafic rocks. Maybe the mafic components of the Levack gneiss. And then lastly, we have this intermediate composition that we are able to observe between the main mass and the country rocks. Thus, we're suggesting here that the sulfides would have first equilibrated with the main mass and then acquired the lead from the country rocks, maybe by thermomechanical erosion. And as you can see here, we have these protoors we were talking beforehand in the Pissing diabase and Eastbow Lake intrusions. And at the end of the day, the Ebly, maybe just like you can see the relationship, they're pretty close. I mean, both of them are the race radiogenic, so maybe there's an influence or derivation. And the same happens in the Pissing. Maybe the south range contact ores have a signature that is derived from the Pissing diabases. So again, we have the strong influence of derivation from footwall rocks or country rocks, or maybe even a mixture. Now let's go into the osmium isotopes. Well, the first thing that we observe here is that basically our ores, or sulfide ores, deviate from the mantle, deviate from the chondritic mantle in this case. What we find though is that we have this binary mixture between the Archean superior province, or Levack gneiss, and the uranium metasediments, and all of our northern and southern deposits fall within the trend. As you can see here, this also happens, I mean, it's observed on here. However, normally compared to the lead and the sulfur diagrams, one of the things we observe is that we don't have this variability or stronger variability in osmium. This is maybe why osmium again was lesser volatile than the other elements, or lesser susceptible again to modification. Now let's explain the problem that we're having with the sulfur content and sulfur saturation, or SCSS. So the big question we're always having is that we don't know the initial content of the sulfide in the melt sheet. It is unknown. So for this diagram here by Lee and Ripley 2004, we have temperature against sulfur in the magma in ppm, and it's presenting two different scenarios from literature. In this case, we have the data or the sulfur content of bulk melt sheet from Lightfoot et al. 2001. Here, Lightfoot was basically assuming that the melt composition was that of QD, and with an average sulfur content of 500 ppm. And we also see another scenario where we have from Kisa Lightfoot sulfur content of weighted average of felsic and mafic norite of around 10,070 ppm. So what do we know around here? That at a temperature of 700 degrees, we are able to dissolve in our melt 1600 ppm. However, if we have this content of 500, in order to segregate the sulfides, we need to cool down our melt sheet up to 1225. We'll reach now the liquidus. And later on, when we even cool it down further, we can reach at around 1188 OPX crystallization. However, if we take the other scenario and we get the average sulfur from Kisa and Lightfoot of 1070 ppm, we only need to cool our melt sheet down to 1500. In this case, what we're having is that we are driving sulfur saturation prior to reaching the liquidus. However, for a scenario, we were talking about possible devolatilization of sulfur that we have been observed, or it's suggested with the isotope data. So we're suggesting that we have even lower sulfur content. And if we take it over here, we'll see that we will never reach saturation in this case. So a melt sheet was strongly undersaturated, or maybe it's one of the models. It wouldn't have never reached the liquidus. Thus, we need another model, okay, that implies that we are taking some sulfur from somewhere else. So brief conclusions is that the sulfur, lead, and osmium and other elements were likely devolatilized during the impact, again, prior to homogenization of the impact melt sheet that you've seen in dust and stocks with the hafnium isotopes. Thus, these elements that we're losing, they are going to be susceptible to modification, and we can study these things. Another thing that we are takeaway is that at superheated conditions, the initial sulfur undersaturated melt sheet would not have reached the liquidus. Thus, we are implying that it's necessary another mechanism to assimilate this ores or the sulfides at the base. And here we are basically trying to study the new model with thermomechanical erosion. This model would also explain these isotopic variations that we saw beforehand. In this case, remember that for the lead composition, mostly the Nipissing signature would have been influencing the south range ores, and the Ebley signature would likely be influencing the north range ores. Again, the iron, copper, nickel, PGE sulfides, the signature would have come again from these proto-ores, and that the variable composition that we observe of the sulfide might be a result of the interaction between the sulfide channel that we were explaining in model 2 with the overlying impact melt. Well, thank you. I hope you enjoyed it.
Thanks, Sandra. That was great. So I think we have time for one quick question. And if not, then we can go on to the next speaker. Okay.
Can I ask a question?
Sure, yeah, go ahead.
Yeah, hey Sandra, good talk. I want to ask you something. Do you think the country rocks, have there been whole rock studies on the country rocks?
Sorry, again?
Have there been whole rock studies on the country rocks, and can they account for the PGE, nickel and copper and sulfur?
Yes, well, there are some studies, and one of these are, I'll just take another. When I had this slide prepared just in case this question was to come up. I mean, these are the protoroids that normally we've been studying the most. I mean, normally we're kind of deficient in the metals here around Sudbury. However, these country rocks, the depiscing diabases, I mean, also including this Shakespeare deposit, for instance, the Eastbull Lake Suit, River Valley intrusions, as you can see here, I mean, they do have some mineralization that could be accounted. And it's one of the things that we are proposing. And again, the signatures of these intrusions, the isotopic signatures also kind of match. However, again, they need to be more studies, but this is the kind of the beginning, yeah.
What do you think the meteorite itself contributed to what you're seeing geochemically?
To be honest, I don't think there is anything left from the meteorite yet.
Yeah, I mean, we know that some of these sulfides contain, some of these meteorites tend to have sulfides in them, right?
Yes.
Do you think there's some component, maybe isotope-wise?
No,
or
I basically think that the whole meteorite mass was devolatilized during impact.
Yeah.
I mean, it normally occurs also in this big impact structures. You don't really find, I mean, if you look into small impacts, okay, around the Earth, sometimes you will able to see some of the remaining meteorite. However, in large impact structures, most of the things are volatile, they're completely missing.
Right.
And if they're missing the nickel and stuff, I mean, definitely the meteorite will be the first thing we're gonna lose.
Okay. All right. That's right.
All right.